Okay, so it's 3 o'clock here in Korea. So I think I will briefly introduce and then start the seminar. 네, 안녕하십니까. 칸델라 코리아 한국 오피스의 안존입니다. 일단 어제 참석하신 분들한테 공지를 했는데요. 교육 기간이 어제하고 오늘 양일간으로 변경이 됐고요. 다음 아카데믹 세션, 3주 뒤에 있을 아카데믹 세션도 교육은 수요일, 목요일 양일간만 진행하는 걸로 일정 변경됐으니까 참고해 주셔서 예, 참석 부탁을 드리겠습니다. 오늘 이제 2일차 교육을 시작을 할 거고요. 퀀텀 컴퓨터 기본과 관련해서 아르노와 저희 퀀델라의 CPO인 장 세널트님이 발표를 진행해 주시겠습니다. 잘 해주시겠습니다. 네, 그러면 시작하겠습니다. Yeah, Arno, you can share your slide and start the seminar, please.
Great. Thanks a lot for the introduction, Doyun. So can you see the slides?
Yeah, I can see your slide.
Great. So for those of you who were present yesterday, so we had a 2 hours session separated in 2 parts. So the first part presented by Jean and myself was about some historical milestones of the history of light and then the history of quantum computing, where they're both really related. And then we introduce like the definition from not that formal definition of a quantum computers with all the properties one use when running quantum computation. And we gave a brief overview on the must-know quantum algorithm that give a speed up. And we finished the first part of yesterday's session about that. Then Shane Mansfield, the Chief of Research of Quandela, gave you an overview of the math behind linear optical quantum computation. You spoke about unitary matrix, boson sampling. You spoke as well about Hong-Ou-Mandel effect, which is crucial in linear optical quantum computation, especially to do CNOT gates. And today, so this what we call the part 1B would be the continuation of the part. So the first session we gave yesterday with Jean, and it would be about an overview of how we do quantum computation with photons. To be a bit more precise, the goals of the lesson would be the following. We will explain how a quantum computer works. Then we'll give some arguments in order to explain why photons are a great means to do quantum computations and how they fulfill DiVincenzo criteria. And after that, we give an overview of Quandela quantum computer, as well as some benchmark of the 1 qubit, 2 qubit, 3 qubit gates, and speed benchmark compared to other well-known platform. And to wrap up the session, we're going to talk about how to go beyond what we call qubit encoding, which I believe Shane explained yesterday, but I will explain again today, and give you a brief example of some NISQ algorithm. As yesterday, don't hesitate to type in question in the chat. We'll be happy to answer them, of course. So how does a quantum computer work? How one implements a hello world on a quantum computer? So first, you need a collection of qubits. So as you may know now, like each qubit can be represented by a block sphere. And here we have, for instance, 4 block sphere, which correspond to 4 qubits. Then we need the ability to interconnect those qubits and then to initialize them. Like, of course, if you want to do some computation on qubits, you need to know where you start your computation. So you need to know you need to have the ability to initialize states. And this is how we represent it. So like in some case it's state 0, in another case it's state 1, the red dot being at the bottom or the top of the block sphere. And then what we're going to do is perform operation as defined by a quantum circuit. So that's what is happening on the quantum processor. So you can either have one qubit operation being represented as like this red point navigating through the Bloch sphere, and on the Bloch sphere if you remain on a pure state. And then we can also have like 2 qubit gates which generate entanglement. So as you see here, like the red point has been demultiplied, so we're now in a superposition of state, but we also create entanglement between 2 different qubits. And we can do that with all the qubits, and mathematically, the object representing like this complex 4 qubit state is a complex state vector. Once we did the operation on those qubits, we need to measure them in order to know what are the results of those. And we need like a qubit specific measurement. And from that, you get, you have a probability to get a specific outcome. Remember like the Born rule. We didn't mention it yesterday, but that's a central rule in quantum computing to know what would be the outcome of a measurement. And here you have a probability of having different outputs. In the first, so after the first set of operation we did and measurement, we get like the bit string 0011. If we repeat the operation again, so we initialize the qubits, we entangle them. Remember they represented as a complex state vector. And then we do a measurement again, we get another bit string of 4 bits, and so on and so forth, until we have enough samples, enough measurements to have information about our solution. Just as a side note, this is a crucial step, the measurement part in quantum computing, because it could be that in some cases you need an exponential amount of measurement, and that what we call like full state tomography in the technical term, and that will kill any quantum advantage you get, since you need exponentially many operations to do that. So one needs to be careful when you implement a quantum algorithm that the number of measurements remains like the scaling of the number of measurements remain low with the the parameters of your problem. And the probability distribution represented by different shots or samples we get can be plotted on with an histogram. That's what we did here. And in this case, like the most likely outcome is the state 1000. And it turns out that for instance, in a Grover setup, when we look at the certain element in the unstructured database, then this element would be the most likely one, which is the 100, meaning the answer of our computations. And this is the full setup. So initializing the qubit, processing the information on those, and then measuring them. And how does it look like in real? So one often uses the term quantum computer, but it's a bit misleading, because you can, by saying that, you can imagine that the quantum computer is evolving and doing computation on its own. The reality is that a quantum computer needs a classical computer to do any computation. So it's more accurate to call it a quantum processing unit, as you also have graphical processing unit, which some tasks will be dedicated to this processing unit. And here what you see on the right is a picture of a superconducting quantum computer that's what IBM has, for instance. Forgot to mention on this slide, this superconducting quantum computer requires cryogeny of up to the down to the millikelvin, whereas in our case we just need 4 Kelvin, which is a crucial difference between these two approaches and a big pro compared to the superconducting approach. But then how do we do this hello world on a photonic quantum computer? So first we need to assert and verify that photons are a great mean to do quantum computation. And indeed they are. So as a quick reminder, a photon is a quantum of light. It's like a single photon is like the fundamental unit of light. It's like a indivisible particle-like entity that exhibits
Oh, I think he just lost the connection.
Yes. Please hold on 1 second. Okay, I don't know.
He's
will,
now joining, yeah.
yes, I will pick up the presentation. He is coming back.
Yes, he's now reconnected.
hello
Arno,
again.
Yeah, we just lost you, yeah.
Yeah, is it all good now?
Yeah. Can you share the slide again?
Of course, sorry about that. I believe the hotel Wi-Fi in Denver is not as good as the one in Massey or in Korea. I just shared the slide. Can you see them?
Not yet. Yeah, now I can see them.
All good. So where, until what point did you hear what I was saying?
You get the definition of the quantum flight.
Okay, perfect. And so photon, they have like, as we saw yesterday, both the particle and wave-like properties, which is crucial also in the in order to do like have some quantum interference. As a reminder, interferences is like a way of exhibit a pattern where you have this kind of wave that is overlapping and you have like other constructive or destructive interferences. And in quantum algorithm, it can be used, for instance, let's take a Grover again, where like the element of your database that is not the one that you're looking for will destructively interfere, whereas the one that is the answer you're looking for will constructively interfere, making the probability to detect them high. Of course, we have superposition with photon by just sending them through beam splitters, but we'll come back to that later on. And then we can entangle those photons. So again, entanglement is like a really peculiar property. I like to talk about entanglement using an analogy that I heard from John Preskill, the Caltech professor in physics. So entanglement is like you can think of like a state, an entangled state as a book. So say you have a class where if you take a classical book, you with 100 page, you can like separate those page and give it to different people. They would read a page, share the information with you, and then you can reconstruct the book, this classical book out of the information these people gave. If you try to do this with a quantum book, and if you like try to separate this entangled quantum book with 100-page quantum book, and which each page entangled between each other with 100 people, and they try to read what's happening, well, they would just read like random gibberish on each pages, because I mean that's what entanglement does. Like, you need to look at the book as a whole. You need to look at the 100 page at the same time in order to have like the information about the system. If you look at it like separately, at each page separately, then you won't get any useful information. The worst case, the best case, you just lose information about the quantum entangled state. And so that's a little animation of how we create superposition with photons. So we have a photon source that you can see on the bottom left, which is the red triangle, that's going to send photon on these beam splitters. And so you have a 50% chance of being reflected and a 50% chance of being transmitted. And this means that you either with equal probability you have 50% chance of being detected in either of the detectors or the output. And so this is how we create superposition. Then how do we create interference? So we start by creating superposition, and then we apply a phase shift. So we move like you can imagine it as like you have a wave and you shift the wave so that it's it will constructively or destructively interfere with the other wave, so that it's either detected in one photon when you apply the phase shift, in one detector when you apply the phase shift, or with the other detector. So that's how we do superposition interference with photon. Then a little animation to remind you about the property of this wave-particle duality of photons. So first, we send like a quantum object on a double slit. So that's the famous double slit experiment. So we send, say, I don't know, a photon on these two slits, and we have like a probability of this photon being located in either of these two slits. And if we do this experiment, we realize that, and repeat it over and over again, we realize that we obtain an interference pattern. So you will see some fringes where the quantum particles will have constructively interfere, and then some dark fringes where the quantum particle will have like destructively interfere. So this means that, well, we send a photon, which at some point we thought was a particle, but as it exhibits some interferences, it shows that it's also a wave. So this is it for the main quantum properties and how to how to use this and exhibit these quantum properties using photons and linear optics. Then another important point is that there's at least two main ways to do quantum computation with light. So the way we use at Quandela is using single photons. So we call that discrete variable quantum computation. And the information is encoded on the single photon. We know since 2001 that there's a universal scheme for linear optical quantum computation, meaning that with single photon linear optical elements, we know how to do like a universal set of gates, like a Clifford plus a C0 and a T gate. And Also, we have a roadmap towards fault tolerance. For those of you who are pretty curious, we published last week a blueprint of what could be our architecture of a fault-tolerant quantum computer. We can also use measurement-based quantum computing. That would be another way to do fault-tolerant quantum computation. Maybe I shall remind what fault-tolerant quantum computation is. So today we're in the NISQ era. So the NISQ means noisy intermediate scale quantum. So for the device that have some noise, so whenever we ask the system to do some computation, to do some operation, in some cases it happens that the photon is flipping by itself, or we have some errors happening. And we have intermediate scale quantum, so like a few, like thousands, I mean tens to hundreds, even thousands of qubits. And then there's another era, which is the fault tolerant era, where we don't have error anymore on the qubit. Like we know how to correct these errors, like we correct them today on the classical device you're listening this conference on, and so that would be like another era where there's of course a lot of expectation of how all the value that's going to be created in quantum computation. And also, like there's been a lab demonstration of up to 20 photons using so single particles in 2019 by the Chinese group of Zhang Weipan. The other approach in quantum photonic quantum computation is using squeeze state of light. So this one we call it as well continuous variable for quantum computation, photonic quantum computation. Here the information is encoded in the field characteristics, so it might be the amplitude or the phase. It's suited for a task called as Gaussian boson sampling, which is related to boson sampling that you saw yesterday, but slightly different. Like mathematically, you know, instead of computing the impermanent, you compute the Hafnian, which is a different function. Protocols are very sensitive to optical losses, so that's a big con for this approach. And as far as we know, there's no fault-tolerant protocol for this approach. It's still under development and theoretical validation. And now let's move on how to build a quantum computer with single photon. So you may have heard of the Vincenzo criteria. So these are requirements to build a quantum computer. There are 5 criteria in order to build one. The first one is to have a scalable physical system with well-characterized qubits. The second one is the ability to initialize the state of the qubits. So we need to know with what state we begin our computation with. Then we need long decoherence time. So the decoherence time is the time with which like the quantum system keep its quantum state intact, like is remaining as you wish the state is. And that's crucial to have a long coherence time so that we have enough time to do operation on it. Then in order to have a quantum computer, one needs to have a universal set of quantum gates. Quantum computer, or I should say a quantum processing unit. And then one needs to have a qubit-specific measurement capability. And it's pretty nice because we fulfill all of these criteria with a discrete variable photonic quantum computation. First, and we'll show that in the next slide, we can encode qubits with photon. And it's pretty easy. There's even several ways to encode photon as qubits. We say that photons are hyper-encoded. Then we know how to generate single photons on demand. So we just press on a button and then a single photon is coming in. And then we just put it wherever we want in order to generate the state we desire. We don't have decoherence with photons. So we have we have infinite, so to speak, in long decovariance time. But we have other types of noise. We're going to mention it, but such as loss. And we have a universal set of quantum gates manipulated single photons. So remember, it's this 2001 paper or 2001 paper by Knil, Laflamme, and Milburn. And we know how to detect single photons, so that would be our qubit-specific measurement capability. And let's see how each De Vincenzo criteria is fulfilled in a bit more detailed manner. First of all, with discrete variable, like with single photon, we have several ways to encode the qubit. So as a reminder, qubit is like a two-level quantum system. So it's the analogy of a bit in quantum computation. It allows us, and that's why quantum computation is so strong, to have complex superposition of two basis states. And that's represented again in the block sphere, as you can see on the right of the screen. And you can encode the qubit in several degrees of freedom of a single photon, maybe the polarization, the time, the space. What we chose at Quandela is the dual rail encoding, or encoding the information in the space. We chose that because it's pretty easy to integrate that on the chip and do is to make really compact system. And so what's more specifically the encoding? So we take one photon and two what we call optical modes, or we also call them waveguide, or we also call them like fibers. These are represented by these two blue lines that you see here. And if we send a photon in the upper waveguide or the upper mode, it's a qubit in state 0. If we send a photon in the lower one, it's a qubit in state 1. And then if you want to do, for instance, a Hadamard gate, you just have to send this photon that is in the upper waveguide, so in the state 0, on a beam splitter. So after that, you have 50% chance of being in the upper waveguide or 50% chance of being in the lower waveguide. So it's represented by the state 0 plus 1 written here. We should have normalized it with the square root 2. And so we have qubits. Are we able to initialize the system? Well, yes. So how to do that? Well, ideally, we have a perfect single photon source. So we are close to that. And in this one, I'm going to explain what the brightness of a source means. So in the ideal case, whenever we press a button, we have one photon and only one photon coming out of this single photon source, which is represented by this wave every time. But in reality, you get a probability of getting a photon whenever you ask for one. And this is the definition of a brightness. So if we say that we have a brightness of 50%, we have one chance out of 2 to get a photon when we ask for 1. And then, so some more properties of single photon that I believe you already discussed with Shane yesterday, especially the Hangul-Mandel effect. So the second one is purity. So as I mentioned, when you ask for, when you want a single photon, you just want, as the name implies, one photon, you don't want 2. And so in order to check that, you send what you think is a single photon on a beam splitter. And if it's just one photon, then you put 2 detectors on the 2 paths outgoing from the beam splitter, then just one detector will click. But if it ends up that you have 2 photons, in some cases, you will have 2 clicks. So you will know that you have 2 photons, and this you don't want. So we're looking for a G2 as low as a G2 of 0 as low as possible. So we're looking for a really high purity. Another crucial properties of our photon is that they have to be indistinguishable in order to do quantum computation, meaning that one cannot tell which photon is which. And in order to do that, we perform an experiment designed by Hangu and Mandel. So we send two photons on a beam splitter, and if these two photons they're indistinguishable, then they should either come out both in the upper mode or both in the lower mode. So we should have only one click in either of the detectors. If it happens that we have two clicks, it means that these photons are distinguishable, and this we don't want. So again, what we're looking for is for high indistinguishability or really low distinguishability. So as you may have understood, what we're looking for, like the ideal single photon source to initialize our state, is a source with a high brightness, high indistinguishability, and high purity. And well, how one shall do that? So there's two main approaches to generate single photons. The first one is using what we call a frequency conversion method. So a SPDC source for a spontaneous parametric down-converted source. So it's a method where we have a nonlinear crystal that is being shined by an attenuated laser. And by doing so, we can, so with a really nice demonstration, we can show that you will get at the output with some probability two photons that one will be used as a herald signal, as a herald photon, in order to declare that we have another photon coming out at the same time, and we will use the signal photon in order to do quantum computation. This approach advantages are the fact that it can be done at room temperature. The limitation is that the brightness, well, you need to choose between the brightness and the purity. Like if you want more photon, like a higher throughput of single photon and coming out of this nonlinear crystal, you can do it by shining more light, light with high intensity on a nonlinear crystal. But if you do so, you will have more, the purity would be bad. Like you would get in more cases, it will happen that you will have more two photon events. So two photon instead of one or even three photon. And that's bad because it will mean that you will initialize your state in something that you don't really know what it is. So you cannot do quantum computation with that. So that's the approach used by PsiQuantum, our competitors. What we use at Quandela is quantum dots. So it's an artificial atom composed of thousands of atoms. So it behaves like a single atom, like a two-level atom, where whenever you pump it with some light, it gets excited. And then when it is being de-excited, then it emits a single photon. And this is what we collect in order to do quantum computation. What you see here on the left is a picture with the microscope of a quantum dot. So that's the shining point in between the red bands in here. And this is operated at 4 Kelvin. The great advantage of this one is, unlike the previous approach, you don't need to choose between the brightness or the purity. You can have either a high brightness and a really high purity at the same time. Also, it's like the manufacturing is harder. And well, at Quandela, we're happy to say that we mastered this manufacturing. That's our major competitive advantage in order to build a quantum computer. And photon collection can be harder than in the previous approach. So this at Quandela, we have a secret recipe for quantum dot-based swirls. They are now fabricated in the, so they come from like 25 years of research from the French research lab called CNRS, and more precisely the C2N, for Center of Nanoscience and Nanotechnologies in Paris region. And so the recipe is the following. We put the quantum dots inside a cavity with mirrors below and on top. And this, the goal to that is to direct the light that is being emitted. So if you don't put these mirrors, this cavity, like the photon is going to be emitted in all directions. But if you add that, then you are able to focus the direction of emission of the single photon, and you increase the amount of photon you collect at the output. So as you see here, like that's the quantum dot. You collect them thanks to this cavity, and then they're being collected and goes into a fiber. Again, that's a photo with an electronic microscope of what we call a micropillar, and you have the quantum dot inside this micropillar. This is how it looks like in real. So we have the quantum dot is located on this, just above this golden chip. And then we developed a technique to put a fiber on top of this golden chip in order to collect the photon really efficiently. As I was mentioning, so one needs long decoherence time to do quantum computation according to the Vincenzo criteria. We don't have decoherence issue with photons, but we have other types of noise. So as I was mentioning, the perfect single photon source is like 100% brightness. You get a photon every time you ask for one. All the photons are indistinguishable, and you always have one photon when you ask for one. You don't have more than that. And anything that is lower than this 100% is noise. And this noise most of it comes from, so indistinguishability comes from, well, it can be, some phonon noise, like we have some, particle of noise of sound that is coming and interacting with the source and make the photon distinguishable, for instance. But the main source of noise is photon loss. We have loss in the fiber, so photon gets absorbed by the fiber. You also have loss whenever you're in free space and you try to focus the stream of light into a fiber. This leads really impossible to have 100% accuracy with that, so we have some loss here. Like any linear optical elements can also absorb some photons. The chip on which we do the quantum computation that we'll see just after is also lossy, and last, the detectors, even though they're not, the loss is really low, still is 5%, so that's not negligible. And this is how it looks like in the lab. So you saw extensively yesterday what a beam splitter is in mathematical term. Here you can see what a beam splitter is in real life. So that's how it looks like. And then we have a bunch of mirrors, polarizers, and we put all these optical elements on the optical table in order to do like the either some operation that you want to do, and this is how they're being manipulated. Again, as a reminder, we have a universal set of gates with discrete variable photonic quantum computing, since with these two guys, so with a beam splitter and a phase shifter, you can basically encode any circuit, linear optical circuit. So as a reminder, that's the unity matrix for beam splitter, and that's the one for the phase shifter. And if you put a mesh of those, if you assemble in a smart manner, then you have like a universal interferometer that can encode any linear optical operation. And this is how our chip looks like. So previously I showed that slide where we have on the right a optical setup, but that is in a free space. Well, we can do this stuff on chip because we chose the path encoding way. And this is how the chips look like. So that's the golden plate. And you have some fibers coming in here on the bottom left and going out on the top right. Same here. And then you have other wires that, well, Nicolas, just after this 1 hour session, we talk about it, which are electronical contact in order to, well, implement the operation you want on the chip. So these chips are reprogrammable, they're universal, so you can do any unitary on this one. So in order to control what you want to do, you have these electrical connections. And we design our own chip and then ask supplier to produce them, such as Serality, Ligantech, QX, eForce, Ultraloaders, and so on. And that's the universal interferometer I've been mentioning several times now. So as you see, it's a repetition of one pattern. So we have what we call a Mach Zehnder interferometer, which is just two beam splitters, two 50-50 beam splitter and two phase shifters. And then we put them in a mesh. So you see that we have this one here, you found it here again, and then here again, and so on and so forth. And that gives you a universal interferometer, essentially. And that's the chip design we use for our 6-qubit quantum computer. So 6 qubit, we input 6 photons, and we have 12 wires. And then we need a qubit specific measurement capability. So the two main category of how to measure photons, single photons especially. So you can either use an avalanche photodiode, which is based on semiconductor using photoelectric effect that converts light into electricity. It's not that suited for single photon. You can measure like you can resolve the number of photons, tell how many photons you have, but that's a pretty low C component, so one does not really want to use that to have efficient quantum computation. Instead, we use SNSPDs for superconducting nanowire single photon detector. So they're a nanowire made of a superconducting material such as niobium nitride. And the nanowire is typically like a few nanometer thick and a few micrometer long. And it's cooled at a very low temperature in order to exhibit like its superconducting state and reach its critical temperature, so that whenever a single photon is coming in, it will the material will absorb it, and it will enter in a temporary non-superconducting state. And this will be able to detect thanks to the voltage that we measured this detector. The efficiency of this one is like up to 95%, and we have a low dark count of 1,000 Hertz. So dark count is a count. So we think we detected a single photon, but there was none. So it happens like at a frequency of 1,000 Hertz. It seems a lot, but if you compare it to the frequency on which with which like single photon arrive, it's really, really tiny. So we have megahertz photon that are arriving at megahertz. So as the ratio between these two is huge, that's no problem. And these are the main ingredients of our photonic quantum computer. And we just showed how we fulfill these 5 DiVincenzo criteria using a quantum dot single photon source, linear optical element, and SNSPDs detectors. Now let's move on to the overview of the setup. You saw the different part, but how does it look like all together, and some benchmark metric. So this is our quantum dot source that emits one photon every 12 nanosecond. Yeah, almost every, it's being excited every 12 nanosecond and emits one almost every 20 nanosecond. And then we send it into what we call the demultiplexer in order to demultiply the stream of photon from one to several stream. And then it goes onto a chip. Here it's in free space, but that's a mesh of beam splitters and phase shifters that's going to implement the unitary metric we want. And then we're going to measure where we detected photon and store this correlation in order to interpret them and deduce what is the result of our algorithm and solve, as we just showed here, like differential equation, for instance. And this is accessible on cloud.quandela.com, free of charge for now. Don't hesitate to give it a try and ping us if you need any help. And that's a scheme of the setup again. So we have a pump laser, so at 80 megahertz regime that shines some light at the single photon source, and that in return emit a photon. Then this photon needs to be filtered out from the excitation laser. And once we have this stream of photon, we need to demultiply it through the mid demultiplexer. And as one photon will come a bit before the other one, we need to add some delay in order to synchronize all the photons so that they arrive at the same time on this on the chip where the computation, the information is being processed. Again, that's the universal interferometer setup scheme, that we used, and is being controlled by 126 phase shifters by this software called Perseverance, which is our software development kit to compute on our quantum computer. And then we send the photon of the output to SNSPD, so single photon detectors. And we measure the correlation and store all the memory, all the correlation in some memory, and then interpret all the correlation in terms of a result of our computation. Few benchmark. So we tested, we measured the 1 qubit, 2 qubit, and 3 qubit fidelity on our device and compared it to IonQ, IBM, Krito engine, and Rigetti Aspen machine. And we got like a really close to 100%, so 99.6% accuracy for 1 qubit gate, which is like the best in the benchmark. 2 qubit gates of 93.8%, which is super nice as well, and 3 qubit fidelity of 86%. So you see that we are like second in class, just behind IonQ, but better than the superconducting machine. In terms of speed for the 2 qubit gates, we can see that we are a bit slower than the superconducting one, like 1 order of magnitude slower, but we may much faster than the ion one, like 2 orders of magnitude faster. And so that's crucial because there's many algorithms that needs it to be fast, such as variational algorithm. And for this reason, and as ions are really slow, it costs a lot to run such variational algorithm where you need to change the setup and do measurement again and change the setup again. I will be more explicit and detailed about this variational algorithm later on in this training. Another really important statistic is that our quantum computer availability is above 90% on a 6-month period, which is huge compared to any other platform. So it's really robust and reliable quantum computer that we have. And last but not least, beyond qubit encoding with photons. So as we explained, we can encode qubits using photon. So we take 2 wires, 2 modes, we input and we send photon in both of these wires. So in this case, what we call the state 1010, which corresponds where we have a photon, it's mapped to the logic like the qubit state 00. And then we make it evolve using beam splitters. And you see that you have different output, different output that you can find. So one is you can either have a photon in mode 0 and 2, which is the logic state 00, so we know what's the result in this case. Or you can have a photon in mode 1 and 2, and that's the logic state 10, so that's great. But in some cases, you can end up having two photons in mode 0, one in mode 0, one in mode 1. And this, we don't know how to make sense of that in the qubit encoding that we used. So, and that's the limitation of this qubit encoding. Like we taking photons and forcing a behavior they not naturally fitted for. And in order to fix that, we just throw away the ones that we don't really know how to address, such as this one. So it's a error mitigation technique that a trivial one that we called post-selection. And so what I was explaining is written here. So we don't know how to interpret the fact that we can have a two photon in mode 0, for instance, or two photon, one in mode 0, one in mode 1. And for now, we do post-selection in order to fix that, but that's not really efficient. As well, if you try to do 2 qubit operation, because of that, you'll see that these are probabilistic in the KLM scheme. So this famous 2001 paper. And that's a problem for scalability, because if you want to have 50 operations that have a success probability of 1/2, then you see that the 1/2 to the power of 50 is really, really low. So the success probability is too low to observe it. And we need like a different model of computing, a more clever one to instantiate qubit with photons. This is why one would prefer to use our platform to do boson sampling. So boson sampling is like the analog of the Galton board. So we just send photon in a mesh of beam splitters, and we look at what sample we have at the output, and we try to predict that. And that's a way to let the photon be themselves instead of forcing them to behave as qubits. This problem is really interesting because it's a sharp p-hard problem. So it's a really, really hard problem. We don't know how to tackle classically. To give you an intuition about that it's because it leverages these higher dimension of a Fock space. So in more concrete term, if you take 3 photons to encode 3 logical qubits, that is mapped to 8 basic states. But you can have much more states if you don't enforce the photon to be qubit. You can have like 11 basic states. And this shows that and it's like the states such as like 30030 that doesn't make any sense with the qubit encoding that will make sense if we let the photon be themselves. And this is why this is also one of the reasons why the Fock space is of a higher dimension than the qubit space, and that's also why the boson sampling is harder. And we have a bunch of algorithms that we develop and let the photon be themselves, such as this graph algorithm where we're able to count the number of perfect matching of a given graph by just computing, so by running a boson sampling experiment on this one. We also able to encode like a variational quantum algorithm. So we take our chip, we have some parameters of the chip, and then given the output distribution we have, we're going to compute a loss function with parameters, with the parameters being the parameter of the chip. We will optimize the loss function to be as low as possible and get a new set of parameters from the chip that we will then update on this on the same circuit, and again compute a new loss function and so on and so forth until we reach a plateau of convergence. And that's nice because by doing so, we exploit the fact that this computing space we're playing with is much, much bigger than the qubit space. It's like scaling at 4 to the power of n, with n being the number of photons, whereas if you try to play with photon as qubit, the size of the system is just of the computational space is just 2 to the power of n. Using this approach, we were able to classify data, so as the moon data set we show here. Another algorithm we did, it's a variational quantum algorithm where we just where we solved in the similar approach the ground state of a molecule. This is typically the kind of algorithm Richard Feynman had in mind initially when he thought of a quantum computer. As a quick summary and to wrap up, so there's three different models to do quantum computing using our technology. So you either use your running encoding scheme, which is theoretically universal but not really scalable. So you can do some stuff, but they will remain on small instances. You can do boson sampling, so it's native photonic, so that's much better. It's prospect for useful quantum advantage. Quantum advantage has been proven using this algorithm, this experiment, but it's not universal. Like you cannot compute solve any problem a quantum computer, any quantum computing algorithm using this boson sampling model. You can also implement a variational algorithm, which harnesses the huge dimensionality of Fock space, which is great. It's native photonic. You have useful application for now, but it remains heuristics. Like you don't always have guarantees of convergence or finding the optimal value, for instance. And the key takeaways for this, the first part of this second session of the quantum mastering quantum photonic computing, is that first, like photons, we do quantum computing at room temperature. We don't have decoherence, but we have loss, which is like the main issue for us. We're able to manipulate them, like to do superposition, create entanglement, do interference, and so on. We're also able to fulfill the 5D Vincenzo criteria, using single photon source for the qubit generation, on-chip room temperature photon for the manipulation, and single photon detectors for readout. And we also studied like the limit of linear optical quantum computation, which are the fact that we enforce the photon not being themselves in a sense. In practical terms, like it also means that we have probabilistic 2-qubit gates. And instead, we can use like more photon-native computation, such as boson sampling or variational algorithm. Thank you very much. If you have any questions, I'll be happy to take them.
네, 질문 있으시면 질문 부탁드립니다. 예. We have one question.
All right. Is it written? Hang on.
I will take this one, Arno. So
Okay.
yes, definitely today the photon loss is one of the main errors that we can find in photonic quantum computer, and the expected solution is what has been done for years in telecom, is to reduce the loss. So it's more technological problem than a real research problem. reducing the loss will allow us to reach a threshold where photon loss will not anymore be an issue for that. We are just on time, so if you have any questions, please put them on the chat, and I will answer them in parallel.